It's time to start. Yeah. Okay, so good afternoon, because just gone 12 o'clock. Welcome to this mini school. My name is Francesco Petruccione. I'm the director of NITheCS, and it's really a pleasure to introduce you Dean Brandt, who is a PhD student in my group. And Dean, I'm very grateful to Dean because he coordinates the micro schools. Yeah, so thank you very much, Dean, for that. You're doing a great job. And not only does he coordinate them, he also offers them some every now and then. Yeah, and today will be a really useful one because he's introducing us to deep learning with PyTorch. Yeah? And this is a super topical topic. Yeah. Yesterday we had in Stellenbosch, it came to an end yesterday, the NITheCS, yeah, which is a machine learning, deep learning kind of school conference. Yeah, and there were 700 people. Yeah, so I'm very glad that we still have lots of people that are interested in introductory courses on deep learning. So Dean, you don't have much time, so just go. Yeah, and the participants know the rule of the game. Maybe at the end of the Dean's presentation, you can ask questions. If it's very urgent, I'm sure Dean won't mind if you interrupt him. Please, Dean, over to you.
Sure. Thank you, Prof, for a very good introduction. And yeah, welcome to everyone to this week's micro school. It's a pleasure to be talking today about PyTorch, which is, as Prof said, a very topical topic because it's very relevant now, especially in the world of LLMs and AI. And even now at Stellenbosch, there was recently the NITheCS, which is all just about machine learning and interacting with different companies that are now focused on integrating machine learning into their pipelines and everything. And I can imagine that many people want to get started, but also don't really know where, or might be quite intimidated by it because it can be quite an intimidating field when you hear about all the terminology and all the different things, and you hear about these supercomputers processing on massive GPUs, all of these deep learning models. And it seems like quite a monumental task, and it is quite impressive to see how computers can learn from data in this way with something like neural networks to be so good at predicting and things and outputting and image recognition and things like that. But it really isn't too difficult to get started with. It's quite a simple thing, especially with PyTorch. It makes it easier than almost it should be. Yeah, so I want to get started just with the very basics, talking first about what is PyTorch and why. So it's quite difficult to talk about machine learning or deep learning tasks in education about it because there's quite a vast range of experience that people might have. You might have just learned about Python and NumPy yesterday, or you might be an expert in the maths of neural networks and just wanting to get some hands-on experience in building your own. So it's impossible for me to address everyone all at once, but I'm going to try and cover that range as well as I can. So what is PyTorch and why? PyTorch is a deep learning library for Python that is very Pythonic, as they say. It makes it very simple to integrate into your workflow and into your understanding of Python, and a kind of a gentle introduction into that to get it very easy to get started with. As you'll see in the demonstration later, it's very, very easy to get started with if you just know some things like NumPy and a couple of the specific terminology that PyTorch uses. And for why PyTorch is quite an amazing tool, actually, is when you think of deep learning and all of the incredible maths that are involved and the massive tensors and matrices and vectors that you put onto these supercomputer GPUs to understand all of this massive amounts of data, then if you know anything about programming languages, then Python isn't really what comes to mind first, because Python is notoriously easy to use, but incredibly slow compared to other things like C++ or even assembly or the real fast compiled languages. But to do machine learning in something like C++, you would be writing code until you blew in the face, because there's just so many things to take care of and so many things to kind of worry about that it's quite a trade-off. Do you want to be able to do machine learning, or do you want to do it fast? And PyTorch is what bridges that gap, because Python is also notorious and more famous for being able to wrap around other bits of software and just make it easier to interact with. That's exactly what PyTorch is. Torch is a library written in C++ and in CUDA, specifically for programming GPUs and other hardware accelerators, as they're called, like tensor processing units and things like that, that Google uses, or even some of the newer AI hardware processing units. So it's written in C++ and Torch to be incredibly fast in performance, but Python wrapped around it so that you can interact with it, because if you're used to Python, then it might be quite difficult to get used to how to define all the bits of memory and the data types and the data structures and everything like that. Just to get started with machine learning, it would be quite intense. But PyTorch makes it very easy to kind of get started with. And to cover all the kind of ranges that there might be of what kind of level you're at when dealing with this, for the people that are just hearing about PyTorch and seeing this demonstration and want to dive deeper straight away, they're naturally, as a very well documented package, there's very, very extensive documentation on all the different parts that you might need from the PyTorch website. And also we've got very good tutorials and quick starts and little explanations on all the different parts of it that you can go deeper into and see all the little nuts and bolts and nooks and crannies that you might want to go into. And for those that are learning about machine learning and deep learning, want to get involved, but you are still catching up with the logical understanding and the maths behind it all and the real context of neural networks and deep learning, there's a very, very good YouTube channel and YouTube playlist that I actually want to recommend to everyone, because it's just incredibly good for an intuitive and easy understanding of neural networks. And that's by by channel 3 Blue 1 Brown, who also has very good mathematical courses and videos, but this playlist specifically is very good on getting started with neural networks in all of its forms. I'll put this link in the chat, but also you can just search 3 Blue 1 Brown neural networks and you should find it. So now okay, first I want to quickly share that, and then we can jump into the Jupyter Notebook where I can show you how easy it is to get started with. So there's that playlist and linked in the chat that you can save for later. But for now, let's go to the Jupyter Notebook where we can start having a look at getting started with PyTorch. So it is quite simple to get started with. Actually, I should go back to the PyTorch website because they have a very good quick start. If you just click on get started, then it offers a very nice way to set up everything here. Because naturally it's built around using GPUs or tensor processing units. You can get started in something like Google Colab, which gives you the option to pick your hardware source but you'll still need to install the right thing. So for here, it gives you a very basic customizable version of installing what you need. You can just usually pick stable, pick your operating system, your Python installation package manager, probably just pip and Python. You can go to C++ if you want, but we'll stick to Python. Then you can choose your version of CUDA if you have it. If you have CUDA installed to interact with your GPU, otherwise you can just do the CPU version because it still runs that way. It's just a little bit slower. And then it gives you the pip install command to get started. Okay, now let's go back to the Jupyter Notebook. Assuming that you've installed it, which you would follow this bit of code to install just here. Torch, Torch Vision, Torch Audio. Torch Vision and Torch Audio are sort of side packages alongside it that enables you to do deeper things with computer vision and audio processing. So you can build neural networks to recognize images, to process images, to categorize them, to deal the same thing with audio things. If you want to, something like Shazam, where you can recognize sound clips from something, they've got Torch Audio as a package. And usually they lump them all together just because they do have some interactions. Like we'll see, will you be using some things from Torch Vision that Torch doesn't have on its own, and then just matplotlib just because we can visualize some more things. So actually I'll restart this just so we can run everything from scratch. And you'll see here with the imports, all we're doing really is getting Torch, the neural network module, Optim, which is for the optimizers, and we'll get to what that means just now. But essentially it's how you then train your model and the kind of pathfinding algorithm that it has to train. Your utils.dataloader and datasets data transforms, that's all about just getting in the pre-built datasets that they have built in. You can load in all your other datasets that you might want to learn on, but we'll be using the built-in ones because they do have quite a nice library of that already set up for us, and some plotting. So now once we've got everything imported, we can get started with what is the main sort of building block of PyTorch, and that is this concept of tensors. And tensors aren't really anything too new. If you're familiar with NumPy at all, it's essentially just a NumPy array. It's just built in a way that makes the interface between your NumPy array and the underlying C++ code a lot smoother. So it's exactly like using a NumPy array. It's just now you'll use tensor or torch.tensor instead of np.array. There are a few other slight differences there, but for the vast majority of use cases, you just use torch.tensor instead of numpy.array, and it does the exact same thing. Yeah, you set it up in the same way of your nested array, like you would in Python. You use it the same way as you would for any other NumPy array. You can even get it from a NumPy array, where you can initialize a NumPy array here and then just torch.tensor your NumPy array, because they are very much the same thing. But the crucial point is that tensors can be put onto your GPU. NumPy can't do that because it's not really built for it, and there are other things that can do that. But tensors go onto a GPU, as you can see here. That it's very important that with Torch you can choose your device that you want things to run on. When talking about a GPU, you usually refer to it as CUDA, because it's the CUDA programming language that then interfaces with your GPU. And as you're familiar with mostly NVIDIA GPUs, they've got what they call CUDA cores, and that's the main processing unit in a GPU. I believe it should work on AMD GPUs, but I'm not really sure. I haven't experienced that. So feel free to try, otherwise stick to a CPU. This also says if CUDA is available and it's set up properly on your computer, then it'll use that. Otherwise, it'll just use your CPU. But here, I do have CUDA set up on this computer, so it says CUDA 0, because you can have multiple GPUs as well, so you can do many different things. And for next is we want to get started with our data set, because we want to have something to do the machine learning on. Here for loading in a data set, there's a couple of things here, but I'll walk it through every little step. First, we just want to define transformation, because when we load the data in, we want it in the right form. And the transform is basically just a list of settings for if your data might be in some JPEG format or just a Excel sheet or something like that, CSVs, whatever it might be, just to put it into a tensor first. But then here is the line of normalize. That just means that it's setting the values between a certain range. Usually you want the values to be between 0 and 1. Like if you have a picture that's in full RGB, then it's going to have all the channels of between all the color values of 0 and 255 for each color channel. But we want things that are between 0 and 1, just because everything's then on the same scale of 0 and 1, that these numbers make sense. That you won't have a pixel value that's 250, then that gets confused with a weight value that's 0.8. And then, yeah, the numbers just don't really work nicely. So you want to normalize everything. As for why these numbers are not 0 and 1, they're a little bit different. This is just kind of a common trick of the trade that's used with specific data sets. People have fiddled around a little bit more and have shared these results online of just what works a little bit better. Rather than doing 0 and 1, they normalize between these values for this data set, because it cuts out a lot of the other noise and just makes it a bit simpler and nicer to work with, and less likely that the algorithm will get confused along the way. So that's the data transform. But then now we are downloading the datasets.mlist. mlist is the most famous hello world example of any computer vision task, or neural network training on image classification, because it is essentially just pictures of 28 by 28 pixel pictures of handwritten digits, which makes it more of a natural task to want to classify the image, because that seems like, okay, well, yeah, it'd be quite impressive if you could train a computer to just see a whole bunch of handwritten digits, then can it eventually recognize it? And that's the building blocks for things like facial recognition or object detection, everything like that. And we'll get into some examples of what MNIST looks like, but it's by far the most common example when used for image recognition tasks. There are similar ones in this datasets module, like the fashion MNIST dataset, which is essentially just pictures of little fashion items like shirts and shoes and things like that. Also 28 by 28 and in 10 different classes, and then used to classify between those. There's also things like Kuzushiji MNIST, which is the Japanese kanji characters that are roughly grouped into 10 different classes. and to see if you can recognize Japanese characters, because those are notoriously also quite difficult to detect. There's also things like EMList, which detects handwritten letters in Roman characters. Many different of these datasets, but that you can find in this datasets module, but you can feel free to explore any different ones of those. For this one, we're just using MList, and this is just how to set it up, that here it will get the training dataset and a testing dataset, and these already been kind of pre-assigned and pre-processed by PyTorch in this datasets package, that there's already a training set and a testing set that's nicely split. In the training set, I believe there's 60,000 training images, and in the testing set, there's 10,000 testing images. So there's more than enough data to train our model on. And then the important concept here is the data loader, which is then how you go from having your data set that you've just downloaded and kept in storage in the file space that you're working in. Then how do you actually get it in a form that you can then put it into this transform and then into the model that you're working on, funnel it onto a GPU and get it in a neat and tidy way. PyTorch does that through a data loader, which just neatly organizes your data in a way that the neural network likes dealing with it. It keeps things modular and separated and just makes it work nicer, but not too much to worry about. You'll write this once, you'll get used to writing it a lot of times, and then things will flow smoothly from there. This is also where we can define the batch sizes that we want to do. And the batch sizes are essentially just a way of grouping a bunch of images or a bunch of data points into little groups or components so that it's more efficient for your algorithm, that it doesn't have to go picture by picture by picture, because you can imagine 60,000 of anything is going to take long. But if it's grouped and batched into sort of these bite-sized chunks, then it's a bit more efficient for your computer to go through, because it will also parallelize that operation, especially on something like a GPU, and do it just much more efficiently. And because it's grouped like that, it's not learning just image by image, but rather learning the general patterns of the images. Like if I give you a picture of a handwritten 7 and I say, tell me what this is all about, but do you know any of this? Imagine giving that to a model, it's going to struggle to see kind of what it's supposed to be looking for. But if you give it 64 different pictures of handwritten digits, then it can start to make sense of, okay, these are the patterns across here. All the digits have this pattern. All of them look like in this way. This is kind of the range of all the different kinds of digits. So it makes the algorithm more efficient by being able to learn 64 things at a time rather than one at a time, for example. But you can set this batch size as anything you want. Usually there's quite a range of things, but people have found what works best in most cases, and they just go with that. This is just a very quick visualization example. This is just matplotlib. Don't worry about the code behind it, but this is what the digits look like. And you can see some of them look not as easy as you'd expect to be able to recognize them. Some of the 7s look quite similar, or they look quite strange like this one. They're usually slanted or twisted or shifted. 70,000 different ways of doing it. Even there's one that has like a bit of a gap in it. These numbers get very weird. You can look at the whole data set to see that it is quite a varied data set of any and all kinds of ways of writing numbers. If a person can recognize it, then it'll be in this data set for whatever extreme. So that's why it's a very good example for image recognition and classification. For the neural network we'll be using, you can use a very basic neural network for this, just a fully connected, the most simple bread and butter neural network that's out there, which would essentially, it'll take this whole image and then just flatten it out into taking it row by row so that it's just lots of numbers along. I think it's 784 or something vector entries, and then passes that through the neural network, which is quite a simple task, but worth trying out to test if you can put your PyTorch knowledge up for a challenge. But we'll be using a convolutional neural network, or a CNN. A convolutional neural network, I can't get into all the details of it because it'll take much longer than I've got for the micro school, but essentially it's a neural network that's based on taking whatever image, or it can go beyond images, but essentially just working on a matrix, and takes this kind of a lens called a kernel and puts it at one point in the image so that it can see not just what's one single point, but what are the points around it. So it won't just go pixel by pixel by pixel, but it'll see what is surrounding each pixel. And it kind of slides that lens along the whole picture to see what's next to everything else. And that's how it convolves through the entire image to then see which images, which pixels are in close proximity to each other. Because if you imagine the drawing of a 7, if you just flatten that out, then you're not going to see that the 7 goes from along the top and then diagonally down, because you're just going to see the vector numbers that are along there, and then there'll be these big gaps in between where there's nothing and then where there's actually some data. So it's hard to see what's in close proximity, and then you can imagine if you have to flatten out that whole big image, it'll be hard to tell apart any of the numbers. So a convolutional neural network usually is used for image processing because it makes it much more effective at seeing what is in proximity to what else. There's also these ideas of max pool layers, and that's essentially just for if you are convolving all these different things and putting it into these different channels with just this kernel that's going around all of this. It's a lot of data to be dealing with because you're adding in a lot more complexity and a lot more numbers to what a simple image represents, that you want to distill the most important and the most relevant parts of the kernel that you've just gone over and the convolution you've just done. You want to distill that into the next layer so that you can convolve around that and then distill it again, just so that it doesn't keep growing and that you don't get lost in all of the little irrelevant numbers, because you'll still have a lot of numbers that just represent the dark spots in the image, and that those don't really do much. So it kind of takes the average of each kernel function and then distills it down. There are lots of different methods and techniques involved here, but that's more in the math side of it and more in the architecture of the neural networks, which I encourage you to go have a look at. But for us, for now, it's just about this simple neural network module where we're going to go through a few convolutional layers and a few max pooling layers before connecting it to a fully connected dense layer of just 128 fully connected neurons. That's just your vector of 128 with all of the different weights from the convolutions, and then distill that down to a layer of 10 as our prediction layer, because it's going to be in one of 10 classes from 0 to 9. And then we see whichever one has the highest probability of being correct, then that's going to be the one that we take as the prediction of whatever image it is. And to put that into code, you can see that the neural network is very simple to write out in a Python form. So it's not about having to go and create all of these complex things and connect all these matrices and all these different points and they're fully connected and having to do these convolutions and everything ourselves. We really just have to make a new class, say that, okay, well, we want a convolutional layer that has this size and this shape with all of these parameters. These numbers you'll get used to if you look at the documentation, but it's essentially one input channel with 16 output channels, and it's got a kernel size of 3 with a padding of 1. So that means it takes in the one channel of this one grayscale image, and it puts it out into 16 channels that we're going to convolve over in the next part. But the kernel is of size 3 by 3, so it's a 3 pixel by 3 pixel square. But you can kind of imagine that when you get to an edge of an image, then if you want to look at the very corner pixel, then you can't really see what's outside the corner in that 3 by 3, because that's just centered there. You're going to miss the 3 on the side and the 3 on top. So it's got a padding just to make sure that you won't start at the very corner of the image, that you'll start one in, so that even all the rest of your kernel is still filling out that block. There's better visualizations for it, but that's essentially the summary of it. If that didn't make sense, then that YouTube series that I linked you to is going to be very useful for that. So there's the 2 convolutional layers that we've defined. We've defined our max pooling layer here, which then just defines how it distills everything down. Our fully connected first layer, where it takes that many input channels and then 128 outputs, so that it's got 128 as its final weight vector, and then another final one where we take 128 down to 10. Then we just have to create this forward method, which just tells us that, okay, well, we start with X, whatever data is taken in. It puts it through this convolution. That puts it through an activation function, this ReLU or rectified linear unit. You can go into much more research about the activation functions, but essentially that's just what takes it from, in a neural network, if you just pass the data through, it'll just end up adding numbers together. But you need an activation function to map it into something non-linear so that it can actually explore a bigger space of numbers and interactions between all the numbers in the different weights. So an activation function is just what gives it really its expansive power. And then we put that through a pooling layer, and we end up with X. And then you do the same thing for the next layer. You put the convolution method, the ReLU, and the pooling. And then those are your 2 convolutions and max pool layers, just like that in 2 lines. We flatten it out so that it can be just in a normal fully connected layer. Then we put it through our first fully connected layer, that one that gives 128 output channels through the rectified linear unit activation function. And then finally, we end up with this final layer, this layer of 10 outputs. And then you just return that answer. And then there you go. This is what people are talking about when they say that PyTorch is very Pythonic, that it's very easy to read through and set up like this, that you can just set up a class very easily with these methods and then nest everything like that, line by line by line. It feels very much like Python. You don't have to worry about all the different jumping through the code hoops that you need to do in other languages. But it feels like you're just working with Python here, even though deep down you're working with C++ and CUDA. Finally, here we put in this, you take your CNN that you've defined, and then you have to put it to the device that you've initialized. And that'll either be your CPU by default, or if you've got a GPU set up and you selected device equals CUDA a little bit further up, then this will just put the whole model onto the GPU ready for the data. So when you put the data on the GPU, then everything's there and it processes all in one place. Now with that set up, we can start training the model. And for training, it goes through a couple of important points for us to mention here. The most important here is the definition of a loss function and an optimizer. And the loss function is just a measure of, you can see, you end up with a prediction. You want to know how far away is that from the truth and which way you measure that. There's a few different ways to do that. The most usual, regular, default one, there are things like mean squared error or mean absolute error, but those are more useful for just normal number-based neural networks. For something more involved like this, we use the cross-entropy loss. And there's a bigger mathematical definition for it, but essentially it's just the overlap between two probability functions. That's the gross oversimplification, but we can then see how big this overlap is, and then that's what we use as our error distance or our loss function, just to see how far are we from being fully accurate. The optimizer is the function that we go through to change the gradient, change the weights as we tweak the dials in this neural network to then end up with something that is accurate. Usually you'd use something just like a simple gradient descent. But here, Adam is a very popular algorithm that just does that in a nicer, smoother way that doesn't suffer many of the things of either your gradient just getting stuck in a local optima or just hitting a weird number and kind of exploding and going all over the place. But it makes the learning process very smooth. And we'll see what that means or what that looks like just now. Then most training loops look quite similar. You just set up this number of epochs. An epoch is just one full run through of all of the data. But you can imagine when you start with the data and then by the end of it, then you're going to be much better at the end of it than at the start. But when you can go through it again and then look at that first bit of data all over again, you're going to very quickly learn much more effectively by carrying over that learning from the first time that you saw it. So a number of epochs is just how many times the model gets past all of the data in sequence. You just associate these lists to keep track of everything that's going on. You set the model to training mode, and then you go through this training loop where you put the data and the target of the actual image and then the image category, because of supervised learning, you're going to have the data and then its label. You put those all onto the device and you instantiate here, or here you define that the output is what happens when you give the model the data. You put it through your loss function, you see how far away you are. You run this dot backward for it to do its back propagation and calculation of all the gradients and seeing how much all the weights have to change. You run your optimizer, and that then calculates all of the gradients that you need to and makes the changes to the different weights. You track what your loss was, and then here is just we're keeping a list of it so that we can visualize it afterwards. Then by training it, you can see that it starts out here, epoch 1, batch 0 with a certain loss, and then it trains through and the loss gets a bit lower and lower. Epoch 2, same thing, it goes batch by batch and gets lower and lower. But as you see by the training loss curve, that this model learns quite quickly. It starts out not very accurate, but very quickly it drops down to very low loss and then hovers around there. You can configure something that early stops your algorithm, that if the loss doesn't decrease by a certain amount within a certain number of steps, then you can just cut it short, because you can imagine how much time it would have saved. not really in this case because it was quite quick, but if you're training something that could take 20 hours, but it reaches its lowest loss after 20 minutes, then you wouldn't want to waste all the rest of the time just hovering around that point. But for this case, it did train very quickly and just stayed around there. It wasn't improving. But that's a very good sign that it did train very quickly. And this is, for anyone familiar with any loss curves or optimization, then you'll see how satisfying this can be, that someone can learn this quickly. Then we want to evaluate it. We want to put the trained model onto a test set. So now we can switch it to model.eval so that it actually evaluates instead of trains. And then you establish all your counters and all of your lists. Here we put this with torch.nograd wrapper around everything, just to say that don't update any of the gradients, or don't update any of the, don't even include gradients into the tensors, because there's not going to be any gradients being calculated or any changes being made to the network. This is just put the network onto that, get a prediction, see how good the prediction is. So this is quite a bit shorter. And here again, the line where I talk about that you'll end up with your 10 outputs, and then each one of those will be a number between 0 and 1 as a probability. But we want to take the one that's the most probable. Like if you have that number that was 7 slanted on its side, it might look like a 1, it might look like a 9, so there's going to be a certain probability there, but a good model will then pick it out that it's got the highest probability in the class of 7. And then that's kind of its confidence rating of the probability. But for here, we just take whichever one's the highest, and we select that as our classification value. We see how many we've got correct based on that, and then we can create an accuracy. And here we see that it was 98% accurate, which is quite staggering for what these look like. Some of these look quite insane, really hard to pick out, but to then get a very simple neural network with just 2 layers in just a few lines of code in this one simple notebook, we can train a model to see any handwritten digit of this size, and in grayscale, with 98% accuracy. That's quite an impressive thing that you couldn't do in any other kind of algorithmic way. You'd need a neural network for something this simple and this effective. And you can see how easy it is to do in something like PyTorch, rather than having to climb into all the different CUDA coding and programming your GPU and configuring matrices and backpropagation and gradient descent algorithms. Here, PyTorch takes care of all of that for you. This might get you kind of very excited and wanting to see a lot more of what it's capable of. It's unfortunate that we're not building an LLM here, but this is the building blocks for that. So you can see how quickly this can escalate into then building something like a transformer network or a generative adversarial network, where you can create image generation, things like that. All of it's to do with neural networks, and then all neural networks are built like this. In PyTorch, it's very simple of just creating that class that has all the different layers, and then saying what order those layers go in, then adding in your training loop, picking your optimizer and your loss function, and running it through that loop. And that's really all there is to dealing with neural networks and deep learning in PyTorch. So it makes it very accessible and hopefully much easier and less intimidating. That's pretty much all I've got to share from the notebook. Everything else is accessible from the PyTorch website. There's very good YouTube tutorials on the deeper maths behind neural networks and the matrix, the linear algebra, the differential calculus, all of those deeper parts you can find somewhere else. But if you just want to get started with machine learning and PyTorch, then hopefully you can see how easy it is that you can learn it in 20 minutes and be on your way, telling everyone that you're a PyTorch expert, because it's very easy to be an expert in something like this.
Yeah, Dean, thank you very much. It was really a nice lecture. Will you make the notebook available?
Sure, I can put it on Google Colab and then share the link with that for the YouTube video when this is uploaded.
Perfect. That would be great. Are there any questions from the participants? Everybody kept a very low profile, listening very attentively to the wisdom of Dean. No questions. You're welcome to use the chat if you don't want to speak.
Yes, and hopefully I was clear with everything.
No, it was very clear. I followed it, and it was. There's a question in the chat by Joe Marie. Will you please elaborate on what is meant by a gradient?
Yeah, so gradients can go very deep very quickly, but within this context, then I'll quickly explain it. Just that A gradient is sort of if you look at what number you have and then what number you are looking for. So what number would be what value did your neural network, did each weight have, and then what value would it like to be? When you're looking at this loss landscape or seeing where you are relative to where you'd like to be, you want to minimize your loss. So you want to make it as that the difference between what you have and what you're getting is as low as possible. The gradient is just kind of, if you imagine this as sort of this bumpy landscape, you're going to go from where you are down to the lowest point. And the gradient is sort of the angle of how steep that drop can be. So you want to follow that gradient. You want to go the lowest point to the fastest. And the gradient is the mathematical way of then seeing where am I now, and then where would be the next lowest step be, and then going in that direction. And PyTorch does all of those calculations very quickly and very efficiently for you. And something like backpropagation passes all of those gradients into all of the different weights to then tweak it by a certain amount in a certain direction, either increasing by a certain amount or decreasing by a certain amount to make it one step closer along that slope to get to your lowest loss as your optimal point. So things are as similar as possible, your predictions to the truth. I hope that covers it in this context. Yeah.
Yeah, no, thank you, Dean. And Emmanuel asked now, how do you keep track of the best parameters in PyTorch so that the model can use them at prediction time?
That's a good question. And another beautiful part about PyTorch is that it takes care of all of that for you. You don't even really have to make a list like that. It keeps track of everything. It trains the models and keeps track of all of the different points that it goes through and all of the different evolutions that it goes through and all of the different computations that it goes through. And when it trains the model, it only updates it for the best model if it's going to actually be the best model. It still runs through all of the updates like normal, but then it only keeps the best performing versions that it obtains. But usually also you'll end up with, if you go through a training procedure, if your training loss goes down and then starts going up again, then you might have done something wrong. But usually you'll end up just going down and down, that your last one should be your best one. But yeah, it will be quite complicated if you want to quickly store your whole model in a list that has the best parameters, just in case your next one is worse. PyTorch takes care of all of that. It only trains it so that the best one is the one that's kept.
Excellent. I think, Dean, we are slowly leaving micro school territory and moving into mini school territory.
Yeah, I've got a few minutes left in that camp.
Unless there are very urgent questions, I would say we thank Dean very much for the nice introduction to PyTorch. And since I see that there were lots of people present, maybe we need to complement it with a TensorFlow introduction or similar, yeah, because